Let's now talk about integration methods, numerical integration methods for differential equations. So in general, the challenge with numerical integration is this balance between the computational effort and the accuracy that you get out of a method. So of course we want high accuracy, and so we're gonna balance the computational time and the accuracy. So we want to increase accuracy, and in general, we want the computational time to go down, right? So one way to increase accuracy is to take smaller steps in any integration method. So we could say our delta t, that's our step, our time step there that we're going to be integrating against or across. We want that to be as small as possible, right, to increase the accuracy. So if we do that, then the accuracy increases, but the computational time also goes up. Okay, so there's this challenge of how big of a time step do you use, and also the other thing that you can play with is the order of the method, right? So as the order the order of the numerical integration scheme it increases. So I'm just saying goes to infinity, not really, but as it increases, right? As the order increases, our accuracy goes up, and actually also the computational time will also go up because it requires more. The higher order method generally will require more calls to your differential equation or the function that contains your differential equation. In our case, it depends on the aerodynamics, the aerodynamic forces on the aircraft and things. So anyway, so there's this challenge of how do we choose the time step and the order of the method in order to minimize our error, or in order to increase the accuracy and still keep computational time at a reasonable level. Okay, so back when digital computers first came online and became a thing and were invented and started to be used for simulation, several people looked at this trade-off between accuracy and order and computational time and things. So anyway, one of the main ones was by a guy named Pope. This was in 1963. He invented a method that was called the exponential method. And then NASA Langley started to use this, I think, just a few years later, and it kind of became known as the local linearization method. Let me just fix that real quick. Okay, so this is a very common method, local linearization, and I'm not going to go through the math here because I'm not going to encourage you to implement it in your flight simulator. Okay, but just be aware that it's a method based off of this exponential method first developed by Pope, and it turns out that this is a second order method. Okay, so this is second order, and in some places in the literature, people have said that this is actually an exact method. It's not. It's second order, so it does have error that builds up. It is exact for constant rotation, but with an aircraft, obviously rotation is going to be changing as a function of time, so we don't have constant rotation. So it's not exact. It's second order. Okay, but it only requires. We're going to make a table over here. So this is we're going to call it the local linearization method. It actually only requires one call to the differential equation per time step. Okay, so we're going to call this the number of computational cycles is the number of calls. to the differential equation. Okay, that's what we're going to call computational cycles, and it only requires one per time step. Okay. Okay, another common method is Runge-Kutta integration. Okay, so and Runge-Kutta is actually something that's kind of interesting. You can choose the order that you want in a Runge-Kutta integration. So the traditional one is fourth order Runge-Kutta. I'm sure you've had a course or something on, have coded up Runge-Kutta integration fourth order. That's probably the most widely implemented integration scheme. But it turns out you can choose lower or higher Runge-Kutta methods. Okay, so we're going to also look at Runge-Kutta second order. If you implement it, a second order Runge-Kutta scheme, so we're going to call that RK2. That requires two calls to the differential equations per time step, okay? Two computational cycles per time step. Okay, then there was another method. Well, and actually, let's just include RK4 here. So Runge-Kutta, you can use a fourth order integration method. Like I said, that's the most common, so we're going to call that RK4. That requires 4 calls to, or 4 computational cycles per time step. So if we draw that out, you're probably familiar with RK4. You have this equation that you're trying to approximate, and here's your time step delta t. We're going to call the differential equations 4 times, once at the beginning here, right here, and then we're going to call it 2 times at delta t of 1/2. So we're going to call it 2 times in here, and then 1 time at the end. We're using all of this information to try to approximate the value at the end of the time step here. Okay, so there are 4. I'll just put the dots in blue here. 4 calls that kind of can be represented like that across that time step. Okay, so that's the fourth order Runge-Kutta. Okay, so there was another method called the Adams Bashforth Moulton method, and this is also a fourth order. It's a fourth order method. We're going to call it the ABM method. So ABM, and this method actually is kind of interesting. So what happens is if we continued on down here, we had another delta t here, and we'll just do one more here, delta t. Okay, so what happens is we're trying to approximate this function, as a function of time, by knowing the derivative at certain locations along that function. And so what the ABM method does is, let's look at this last point here. It actually only needs to make 2 calls, and I'm not exactly sure where in the time step those are called, but we'll just put in 2 dots right here. So it makes 2 calls within each time step here, and then it uses information from previous calls or previous time steps, and so now it has, say, 4 data points here that it can use to make some fourth order approximation for that function. Okay, so it uses information from the previous time steps here. So in any given time step, it only needs to make 2 calls to the function, and then it can combine that with previous information to still remain fourth order. Okay, so that's called the ABM method, and so it requires only 2 calls per time step. Okay, so now what's a little bit challenging with the ABM method is that you can't use that at the beginning of your simulation. So at time t equals 0, we don't have previous information, And so what you have to do is go, I think it's 3 time steps in using another method, such as the fourth order Runge-Kutta or something. So you could go 2 or 3 time steps in and then start to pull information from the previous time steps and switch over to the ABM method for future time steps. Okay. All right. So this is one way to compare the computational effort required here for each of these methods, and remember the order of this local linearization is actually second order. RK2 is second order. RK4 is fourth order, and ABM is also fourth order. Okay, so we have 2 second order methods here and 2 fourth order methods. Okay, so how could we compare the computational effort of each of these methods? Because, see, local linearization only requires 1 call per computational cycle. And so in order to increase the accuracy, you could you could make these delta t's a lot smaller, right? So you could cut those in half, for example, and be making a call for each half delta t here, and that would be equivalent to the 2 calls that RK2 needs in order to be second order. So maybe local linearization is better than RK2 by just making the time steps smaller, right? So in general, that is one thing we can do. We can make the time steps smaller for any of these methods. And so let's just look at the error, the error that we would expect out of each of these methods as a function of time step. Okay, so and you can code up each of these methods and test this out. And basically what you're going to get is, so of course, as the time step goes to 0 for any of these methods, we would expect them to be exact, right? So the error is going to start off at 0, and as the time step grows, the second order methods, so this would be, so this is second order methods, so this would be like the local linearization or RK2 methods, will look something like this, okay? Then the fourth order ABM method is going to look eventually, so its error is going to stay a lot lower for a lot longer, and then come. Actually, let me do the RK4 method first. So RK4 method is going to come up something like this. So I'm going to say RK4 as delta t grows, and then I'll use green for the ABM method here. So the ABM method is also fourth order, and so it also stays low, but it actually increases a little bit more rapidly than the RK4 method. Okay, so ABM method is a little bit less accurate. It's still fourth order, but because, remember, it's using information from the previous time steps and only 2 points of information within this time step here, the accuracy is just a little bit less than the fourth order RK4, for the same size of time steps. But the fourth order RK4 requires 4 calls per time step, and ABM only requires 2 calls per time step. So still, this is not a good a comparison between the methods to try to balance computational effort and accuracy, because RK4 here is requiring twice the amount of effort, or the number of calls per time step as the ABM method. So let's visualize that as well. So let's plot the, let's plot the computational cycles here per simulated second. We're going to say per sim second, okay? And I'll explain that in just a second. And then delta t here again on the x-axis, okay? So so the computational cycles per simulated second. So for example, let's take the RK2 method, okay? And this is a second order method. So let's say that our delta t is at, let's choose 0.1. Okay, so we have 0.1 delta t, and then per simulated second, that means we're going to have 10 delta t's per second, and the RK2 method requires 2 calls per delta t, and so that's going to give us a value of 20 calls per simulated second. Okay, so that would be where the RK2 method is there. And we could compute that for, as we increase delta t, and kind of plot this and see what this would look like, something like this. Okay, so this is for any method that requires 2 calls per time step, and they would fall along that line there. So that's the RK2 method. So we can come back up here. So we've got the RK2 method has 2 calls, and the ABM method has 2 calls per time step. So RK2 and ABM. And local linearization only requires 1 call per time step, so it's going to be at about half of this value. Okay, so this right here is going to be the local linearization method. And then finally, RK4 actually requires 4 calls per time step, so it's going to be at a value twice as high up here. So this will be RK4. That's a K, RK4. Okay, so what this plot is showing us is the computational cycles, or our calls, the number of calls that we need to make to our differential equations per simulated second. And you can see that RK4 is much higher than any of these others because we're making 4 calls per delta t compared to 2 on ABM and RK2, and only 1 on the local linearization method. Okay, so again, this actually isn't a fair comparison either, because this neglects the accuracy. This only looks at the number of calls we're making per time step, and this looks at the error per time step, but neglects the number of calls that we're making. So really, the best way to compare these is actually to take the information here on the y-axis and the information here on this y-axis and compare those. Okay, so we're going to look at here for our final comparison. On the x-axis, we're going to have the number of computational cycles per simulated second. And on the y-axis, we're going to look at the error. Okay, now I'm just drawing this plot and this plot as notional. If you run your own study, this is about what you can expect to get. Okay, so let's look at each of the values here. So second order Runge-Kutta is actually the worst method, and it's going to look something like this. So this is going to be like RK2, the second order Runge-Kutta. Second order local linearization is significantly better, and so we'll put that down here. So that's second order local linearization method. And then it turns out that the fourth order Runge-Kutta and ABM method are almost identical. The Runge-Kutta is just a little bit higher error here, so we'll put this in right here. So this is the RK4. I keep saying R44, I mean RK4. And then the ABM method is just barely below it. It's just a little bit better. Okay, so remember what we're trying to do here, and this is the best comparison that we can make between these methods here, is in a plot that looks like this, where we're looking at the amount of error on the y-axis and as a function of the number of computational cycles per simulated second. Okay, so this is like the number of calls we're going to have to make to our to our differential equation here on the x-axis. So of course, if we make a whole bunch of calls, so that would be up on the right hand side here. So we're taking very small time steps, and then the associated calls for each of these, and then look at the error, the associated error. Then ABM always beats RK4, right? And as we lower our delta t, or excuse me, I'm sorry, we increase delta t, would be moving to the left here, then our error would be going up, okay, for all of these methods. So what this shows is that the ABM method, this fourth order method, is probably the best method for minimizing your error, and it requires only 2 calls per time step. The challenge is that you have to handle the first few time steps a little bit differently. You have to use fourth order Runge-Kutta or something like that anyway for the first few time steps. Well, it turns out that if you just use RK4 for the entire simulation, your error is going to grow just a little tiny bit, but almost unnoticeably. I mean, the amounts here are pretty small. So that's why in this course, we're going to be using RK4 for all of our numerical integration.